You for the introduction and thank you for the opportunity to show my work here. So as Carla just showed, we all like to use diffusion data to get an insight in the structural connectivity of the brain, and it's a great tool for that. It allows us to non-invasively see how the white matter is connected. And if we take good quality diffusion data, so high angular resolution diffusion imaging, hardy data, such as diffusion spectrum imaging or multi-shell cue-ball imaging or even single shell with a high number of directions, we can really figure out the intravoxel crossings in the brain, and we can do nice tractography, see how all the areas of the brain are connected, get to the structural connectivity. A key to all of this is, of course, the orientation distribution function, which kind of translates all of the diffusion measurements in a blobby shape, as you have here. And this blobby shape then points us in the direction of the fibers in that particular location. From this blobby shape, we deduce the fiber directions, which are then used as input for the tractography algorithm. So it's key for a good tractography result to really well identify the fiber directions in each voxel. And this is where we have a problem. If we have fibers, crossing fibers with a small angle, we run into a problem. So suppose we have two crossing fibers at an angle of 90 degrees, then it's really easy to see where these fibers are running, which direction, and we'll be able to track these fibers. If our crossing angle decreases to 60 degrees, we can still see where these fibers are going. And most methods, they just look at the maximum point, the maximum point on the surface of the ODF. However, if we look at fibers crossing at an angle of 30 degrees, these two peaks, who have a certain intrinsic width, they kind of merge, and it's impossible to tell that there's actually two fibers crossing here. You only identify one fiber. So unfortunately, current methods are not really to identify crossing fibers when the crossing angles are smaller than 40 degrees. You can do a little better if you do ODF deconvolution with a fiber response function, but still the small crossing angles are really difficult. So we thought of trying a new approach to this problem of the fiber identification, and we thought of trying some of the key concepts of MR fingerprinting. So MR fingerprinting is this hot new technique where you kind of simulate the MR signal in a voxel with certain combinations of T1, T2, B1 fields, and then by comparing a measured signal with a whole library of these simulated signals, you can get quantitative maps of T1, T2, and so forth in a very short time. We thought of applying the same approach to this fiber identification problem. So basically, we are going to take a whole set of potential crossing fiber configurations. We simulated diffusion-weighted measurements of this and calculated ODF for each of these configurations. ODFs are nothing more than numerical values on a sphere, so you can also represent them as a vector or a trace. So this then forms a nice large matrix. And for each measured ODF, and this ODF they can be acquired by a DSI acquisition or a cue-ball imaging acquisition, or however you want. We also take the vector, the trace, we compare with our library, and from there, if this is the most similar trace, we can deduce that this ODF is actually the crossing of these two fibers, as is shown here. I want to show you in this simulation that this leads to improved detection of fibers and detection of small crossing angles. And I have some computer simulations and some in vivo data sets to show you this. So first, how do we get our library? For this very simple tests, we took up to two fibers with a certain water fraction. We aligned the main fiber along the z-axis because it reduces the number of samples we need in our library. We simulated a range of possible FAs, a range of possible ADCs, and we simply simulated the diffusion-weighted signals of each fiber as a cylindrical fiber, and we added them together. For the Q-space sampling, we took kind of an advanced sampling, the radial DSI sampling, which has 236 samples and 4 shells. and then we calculated the ODFs using the radial DSI reconstruction. For the similarity assessment between our measured or simulated traces and our library traces, we used a simple dot product. And so we implemented this in MATLAB, and we compared this with two ODF maxima search methods. The one is the one implemented in DSI Studio, of which we also have a simple MATLAB version. We also compared to the MRTrix version as implemented in the SH2Peaks tool. And lastly, we also compared to the probabilistic estimation of the directions using FSL's QBoot. Now, in these first results, we simulated two crossing angles with random directions. And then we compared what is the simulated crossing angle here on the x-axis compared to what is the identified crossing angle after all processing. And ideally, we would want the graph to follow the diagonal. And you see, if you look at the DSI Studio and MRTrix methods, which kind of follow, which use an ODF maxima method, they kind of underestimate the crossing angle, and below 40 degrees here, those methods kind of fail, and they only identify one angle, one fiber direction. If you look at the QBoot method, it also does, it overestimates the angles, and from a certain angle, like more or less 40 degrees, it no longer identifies the two intended simulated angles. It only identifies one of them, and it identifies a second non-existent perpendicular angle, so you get this 90-degree crossing angle. Our method, though, the ODF fingerprinting, it follows nicely the diagonal, and it only starts to deviate where it starts to get really difficult to identify the two fibers. So this first row is a simulation without added noise. This is, of course, the simplest case. In the second row, we added noise, and you can see that the conclusions still largely hold. I also want to point out that we looked at the precision of the determination of the fiber direction, and with the fingerprinting, we get a more or less constant precision, whilst with the other methods, you get kind of a loss of precision as the crossing angle gets smaller, and then here the comparison breaks down because they only identify one of the actual simulated fibers. These simulations were a little bit, these simulations were done with the same diffusion model as our library. So we just simulated cylindrical fibers, we added them together. So this is maybe a little easy simulation. That's why we took an open source code which simulates the diffusion in a different way in a composite hindered and restricted diffusion model. This is a Phantomas package. And we can see that here too in the comparison between ODF maxima search and the fingerprinting method that we get good agreement in the tractography. And if you zoom in some of the areas, you can see that you identify more of the crossing fibers than in the ODF maxima search. Of course, the most important part is what does it do in vivo. So this is a radial DSI data set with 236 Q-space samples on 4 shells of a healthy human volunteer, healthy male volunteer. We did this on a Siemens Prisma with a maximum B value of 4,000. And here on the left, there's the two ODF maxima search methods. There's the FSL QBoot, and then our suggested fingerprinting method. And you can see we get a fuller tractography in our method, giving nicer tracts. If you zoom in, you can really see the difference. So just going back, this is zoomed in this area. You can really see the difference in identifying the crossing fibers in this region versus none of the other methods really identifying these crossing fibers. So to summarize, in calculating structural connectivity, the tractography relies on accurate identification of the fiber directions from the diffusion ODFs or from the diffusion measurements. And current methods really struggle if you have smaller crossing angles. And we wanted to apply key concepts of ODF fingerprinting to this fiber identification task. And we've shown you improved detection of fiber crossing at smaller angles while still maintaining direction precision. So we hope that this will help the fiber tracking algorithms to display neuronal tracts and to calculate the brain connectivity. In the future, we want to look into more detailed diffusion models and also in phantom validation to really get an idea of what is the best method. I want to thank my colleagues and funding agencies and you for your attention. Thank you.
Thanks so much for the great talk. If there are any questions, we have time for one.
Hi, I had a question about the fingerprinting. Since you're using a library, how does that translate when you go across scanners or across centers? Do you need to regenerate the library every time for reference?
Well, since we're working on the ODF level, I didn't try different scanners, but I think it wouldn't make a huge difference because we noticed I used fairly similar libraries between the simulations and the in vivo measurements, and they had different B values. So and since we're not fingerprinting the actual diffusion measurement, we're fingerprinting the ODF, which is already kind of a summary and kind of extracts some of that scanner variability.
Okay, and also just, do you also get confidence intervals, like a plus or minus on the angular direction with this method?
No,
Okay.
we don't.
Okay, thanks.
Thank you.
Great, thanks so much. So thank our speaker again.
Thank you.